So in this video, we want to solve a non-homogeneous recurrence relation when the particular solution is not of the standard form. So one of those special cases that we looked at in the last video. So I want to consider the recurrence relation un equals 6un minus 1 minus 5un minus 2 plus f of n, but I want to consider the case where f of n is equal to 8n. So plus 8n. And it's the same as the one we had before. So I'm going to tell you that the solution to the homogeneous recurrence relation is hn equals a times 5 to the n plus a constant b. And we want to consider the particular solution. Well, according to the standard particular solutions, because f of n here is linear, we should consider the particular solution Pn equals an plus b. However, because Pn is polynomial, then what we actually need to do is we need to multiply the particular solution through by n. So we're going to consider the particular solution an squared plus bn. Okay, so let's think about substituting that into this recurrence relationship. So what is Pn minus 1? Well, Pn minus 1 is an minus 1 squared plus b n minus 1, and Pn minus 2 is a n minus 2 squared plus b n minus 2. So we're putting that into the relationship Pn equals 6Pn minus 1 minus 5Pn minus 2 plus 8n. So what do we get? Well, on the left hand side we just get an squared plus bn, and on the right hand side we have 6n minus 1 squared plus 6bn minus 1 minus 5. Oh, I'm missing an a. This here should be 6. 6a minus 5a n minus 2 squared minus 5b n minus 2 plus 8n. And what we want to do is we want to simplify that as much as possible. Well, you might want to do that yourselves, but if we think strategically about it, we're going to get, by expanding this out, we're going to get a 6an squared. And by expanding this out, we're going to get a minus 5an squared. So we're going to get an an squared on the right hand side. And we also have an an squared on the left hand side. Similarly, if we expand this out, we get 6bn. And if we expand this out, we get minus 5bn. So we get 6bn minus 5bn, which is bn. So that will cancel with this bn on the left-hand side. So all we need really are to get out the linear terms from here, and the constant terms from here and here. And we're going to get a 0 on the right-hand side. So we get 0 equals, well, the linear term here is minus 12an, and the constant term is plus 6a. We just want the constant term here, which is going to be minus 6b. And then from here, we want the constant term, which is going to be minus 4n times minus 5a, so plus 20an, and then a constant term of 4 times minus 5a, so 4 times minus 5a, which is minus 20a. And we're also going to get from here, well, from here all we're interested in is the constant term, because we've already cancelled the minus 5bn, we get plus 10b. And then we also have at the end the add 8n. Well, we can now group like terms. So if we start grouping like terms, we get 0 equals, and let's take the n stuff. So the stuff with an n in it, we've got here, here, and here. So we take a factor of n, and we get 20a minus 12a, which is 8a, plus 8. And then what we've got left is all the other constant stuff, which is 6a minus 20a, so minus 14a, and then minus 6b plus 10b, which is plus 4b. Well, this is an identity really, so that must mean this must be true for all n. So that must mean that 8a plus 8 is equal to 0, so a equals negative 1. Well, this constant part here must also be 0, so minus 14a plus b equals 0, plus 4b equals 0. But minus 14a is actually equal to positive 14, so 14 plus 4b equals 0, so b equals minus 7 over 2. Okay, so we found Pn. We know that Pn is an squared plus bn, but we know a is minus 1 and b is going to be, checking that I've done this right, b is going to be minus 7 over 2. Well, finally, to find the general solution of our original non-homogeneous recurrence relation, we need to find the sum of h of n and p of n. So we know that the general solution un is h of n, which is a times 5 to the n plus b, add on p of n, so minus n squared minus 7 over 2 n. And that is the general solution to that non-homogeneous recurrence relation. If you were then given a value for u0, say u0 equals 1, and u1 equals minus 1, you could substitute in these two values, and you could use that to solve for capital A and capital B, so you could then find the specific solution for these initial values.